the slides. Last week I promised to some of you that I will solve this here. So in exercise number 3, you had to obtain the convolution of f and g, which both of them are sine function. And let's see how we can do that. I don't know if you could figure out after the exercise session yourself or not, but let's do it here together. So as you can see, f and g are causal function because it's a multiplication with u of t here. So I can use this formula. So if I do that, here, sine is a function of omega. So first, I will consider if the omega is 0. If omega is 0, automatically L convolve of g of t will become 0. Why? Because the sine of 0 is 0. So it doesn't make any difference in the computation. So this will always become 0. But how about if it's not 0? I mean, omega is not 0. Then L convolve of g of t will become as integral of 0 to t sine of omega tau, then sine of omega t minus tau d tau. So this is exactly the rewrite based on the formula we have for convolution. I think the part which confused most of us, including me, because I forgot how I did it 4 years ago, was how I can move from here forward. Actually, here you need to use the appendix you have in the book. So if you open the file here, and it is here. When you have the sine A times sine B, then we can use this half of bracket formula. So I will use this one here. So L convolve of g of t will become as of half of cosine of omega tau minus omega t minus omega tau. So here what I did, I also multiplied this omega with the parentheses. So that's why I have this as a if I want based on the formula I have. So this is our A and this is our B. So this is the first term minus cosine of omega tau plus omega t minus omega tau. Bracket, I need to close it and then this out. So now I have to take the integration of these. But let's simplify what I have inside the parentheses here and here and here. So this one from here to here, I have omega tau minus omega tau, so these two cancel out each other. So I have only omega t here because these two cancel out each other. And here I have for this to here omega tau plus omega tau, so I have 2 times omega tau minus omega t. And now what I do, first of all, I can bring this half out of integration, and then I will distribute the integration in these 2 cosine I did so far? Now we have to solve these two integration. Let's look at the second part for now, because it's easier. So here, the integration is with respect to tau. And the cosine of omega t is something which is not dependent on tau at all. So what we can do here is that I can write it as minus cosine of omega t, the integral of 0 to t of d tau. And I think this one is very easy. So again, just emphasize on the orange one. So this will become minus cosine of omega t times tau from 0 to t. Which if I put it, it will become, let's do that directly, so it will become t. So I have minus t times cosine of omega t as a result of the second integration. Now I move to the first one. This one is the one which is maybe a little bit complicated, and this integration thing is it's something you have learned in other math course. So for this type of integration, which is not very easy, you can use Maple. So if we use Maple to solve this integration, of course you can do manual as well if you want. It will become, where is my solution? Just a second. One over 2 omega sine of omega root tau minus t. I think that should be the answer, but I will check with the solution we have in Learn as well. And of course, at the end we have to multiply by 1 over 2 as well. But let me check if I have the solution. I mean, for the purple one correctly. So when you have such a problem, one thing we should keep in mind is that if you have a term which is not dependent on your integration variable, it means that you can bring it out of integration. I think you have learned this again before, but just to remind you. So this can come out, and this integration becomes something very simple. And for the other one, if you have something like this or another one which is complicated maybe, then you can use Maple. Well, let me check the purple. I think it's correct. Yes. Any question? Yes, please.
The only thing I don't understand, if I wanted to do the integration by hand, how do I get 1 over 2? That's the only thing.
How from here we can get this one?
Yeah, exactly.
Okay,
I know how you get to sign, but I don't know how you get to 1 over 2.
Actually, I have it here on a paper, so in a break, just come here and I will explain to you. Because I don't want to spend a lot of time on the integration part. Any question here? Good. Another thing before starting is that still I have problem with my Maple, so I cannot run it here. But I have a Maple file in Learn now for you, which later on I want to, hopefully if you can borrow your laptop to me, I show you how you can plot the plots related to the Fourier series in Maple. So maybe later on I will borrow one of your laptops for 5 to 10 minutes, okay? Now let's go to the new chapter or new topic.
So you're gonna pick the root?
Yeah, of course, please do that.
Just just like 10 centimeters up.
A little bit up?
Yeah, we can see the bottom. Yeah. Yeah.
Some part is not clear here. Fine? Now, let's do this. So here, these are the topics we will cover today. So I will define the periodic function first and how we can write or obtain the Fourier series for any periodic function. And then we will go through how we can find the two-sided amplitude spectrum or two-sided phase spectrum for periodic functions. And also the two last ones are some small theories which we will cover. So what is the definition of periodic functions? A function f is periodic with the period capital T. So from now on, if we talk about the Fourier series and you see this capital T, it refers to the period of the function. So it's a periodic function with period capital T, or sometimes we write it as a capital T periodic function if the f for t plus capital T is equals to f of t. A very easy and simple example of periodic functions are sine and cosine functions. For instance, if I plot cosine function, this is one, assume it's a perfect plot. So you can see, if I consider the period of pi and 2 pi, for instance, after each 2 pi, the f of t plus capital T, which in this case is 2 pi, they are the same. So you can see that they have the repeated pattern after each period of the function. So we can write that for f of t plus capital T and maybe plus 2t and 3t and so on, the pattern will be repeated. So this is the plot, I just did it here, and the period is 2 pi. Now I have a question here. For the cosine and sine, we know that the period of the function is 2 pi. How about the sine of 2t? Any idea how it would be the period of the function? Yes, please? Yes, that would be pi. Why? Because you will see that the oscillation or the peak you have here will be closer to each other, so it will become pi. Any periodic function, sine, cosine, or any other ones, which you will see them today and also next week, can also be written in an oscillation form, harmonic oscillation form. So, if you do everything correctly, you should be able to write it as a capital A times cosine of omega t plus phi, which we call this harmonic oscillation format. A is the amplitude of your signal or function you have. Phi is the initial value, initial phase, and in a case which omega is not 0, omega is the radiant frequency of your signal. And of course, the relationship between omega and capital T is this one. So if you have omega of your signal, then you should be able to find the capital T, or if you have capital T, because most of the times it's stated that you have two, for instance, periodic function. Function f, which is a two periodic function. find omega, radian frequency as well. And how you do that? This is the formula, 2 pi divided by capital T. Any periodic function can be written in a Fourier series format. And how you write that? Any function f which is periodic, the Fourier series is equivalent to the summation of n equals to minus infinity to infinity of Cn times this exponential term. What is this Cn? This Cn always called Fourier series coefficients, and we have a formula for it. So if in exercise or in exam I ask you find the Fourier series coefficients or Cn, this is the formula we have to use, which is 1 over capital T, which is the period of function, and you do the integration over the period of function. So in this example you see the period is 2 pi. So you select one period, which I usually take the first one. For instance, I usually take from 0 to 2 pi. So if I want to obtain Cn, it will become 1 over 2 pi, the integral of 0 to 2 pi. Because I take the integration over the period, and that's how I read this. You take the integration over the period of the function, f of t, which function you have, and then e to the power of minus I and omega t dt. When you have the coefficients, then you can put it there. Then you have the Fourier series. One thing which you should keep in mind is that when you obtain Cn, we always consider 2 scenarios. Why we do that? Because by this consideration, one of the computation will become very simple, so I can do it very quickly and put it aside and focus on the second one. So first we will consider if n is 0, and another one if n is not 0. For n0, we obtain C0. Why? Because the formula is called Cn. And when n is 0, it will become C0. And here you have the Cn for it. So again, keep in mind, always for Fourier series coefficients, you should consider 2 scenarios, like what I wrote here. We will solve an example on it in a while, so you will see how I do it as well. Any questions so far? Now let's look at, yes?
Just to be clear, when we have a Fourier series, we have to consider when n is equal to 0 and when it's not equal to 0.
Yeah, when you want to compute the coefficients, Fourier series coefficients,
Yeah.
yes. Always we consider 2 cases. When n is 0 and if n is not 0. Why we do that? Because if n is 0, this term becomes 1. So then you have to just integration of f of t, which most of the time, I don't want to call it, it's very simple, but it's simpler than the case when you have n not equals to 0. So we just make it separate and we will put it aside, and then we focus on the other one. Okay, now let's look at the short video. I think it's around 9 to 10 minutes. Okay, why we need to rewrite, or what's the point of obtain or rewriting the Fourier series of any periodic function?
us go up?
Sorry?
Let us go up?
Anything
Turn
is
the
higher?
volume up?
Yeah.
I will I just muted that. But I don't think it will go any higher, but I will try.
You just need to push the skip button.
Skip.
Oh, it says skip? Oh, I haven't seen it. Sorry. Okay, I will make it higher.
No, well,
I think it's the maximum.
cosine are probably sort of quintessential examples of periodic functions. There's many others. So for example, consider this periodic function. This is what we call a square wave. It's either 1 or minus 1, and it alternates back and forth as well. And this square wave also has a period of 2 pi, which means at any spot that you are, you go over 2 pi and you have the exact same height, exact same function value. Now if I think about these two different periodic functions that I have, well, the one very loosely could be said to approximate the other. As in, if I put up sine of x and the square wave, the one that goes between 1 and minus 1, 1 and minus 1, well, they're kind of alike. For example, the peaks of sine of x sort of are broadly around the places where the function value is 1, and the troughs of sine of x are kind of where that square wave takes the value of minus 1. So there's a little bit of a sense in which you can say that there's a rough approximation, but it's a pretty bad one. And in fact, let me actually just zoom in here on just one period, because it's periodic. It doesn't really matter what happens everywhere else, it's just going to be the same thing. So I'm just going to zoom in between 0 and 2 pi specifically. And so my point here is that sine of x times 4 over pi. Don't worry about that constant just yet, we will get there. But my claim here is that this is a bad approximation for this function that's 1 and then minus 1. So how do I do that? Well, if I wanted a better approximation, okay, it depends on where you are, but you kind of want the green curve to move around a little bit. Some spots the green curve should be a little higher if we want to approximate the square wave, and in other spots it should be a little bit lower. So how do I adjust sine of x to be a better approximation to my discontinuous function, my square wave? Well, take it as follows. What if I take another sine term? This is the sine term, which is the same 4 over pi. Again, let's ignore that. But this time, it's sine of 3 times x divided out by 3. And there's 2 3's here, and they're both important. The fact that it's sine of 3x here means that it's oscillating up and down much faster. And it's oscillating in quite an important way, because, for example, if I look at the highest value of the green sine of x, that corresponds to the lowest value of sine of 3x. So you can kind of imagine if you added these two things together, there'd be sort of an appropriate cancellation. And the fact that there's a 1/3 up the front means that this thing that I'm introducing
Fourier series. So we take a periodic function and we approximate it, rough approximation with the sine or cosine or also summation of those. So let's back to the slide. So as he said, and also I mentioned, this is a rough approximation, and that's why I don't have the equality sign here. It's not equality. And depending on how many many times we do this summation, of course we have the better approximation. So for now, I will show you how we can obtain the Fourier series in this exponential form. And later on today you will see how you can convert this exponential form to this cosine harmonic oscillation format. But as I said, you can also do it as a sine format, like what he explained. But both, or we have also the summation of those, so all are possible. Any question? Because I want to go to the example. Yes?
Just in the example, we had 4 over pi. Was that the amplitude of the function, or?
These are the Fourier series coefficients.
Okay.
So now I have an example here, which where is it? Here, which I will solve it in a board, so it will become hopefully clear after this one. And you?
Yeah, I was just looking. What's it called? The Gibbs phenomenon.
Yeah.
Would it be the more times you do, would that be?
It will
Will it
become
be
better
more,
and
or
better. Yeah.
Also the
Yeah.
offset.
Yeah,
by
that's
around
why if
zero?
you do this n, or do it for instance, instead of doing from n equals to 1 to 10, do it from 1 to 1000, of course you have a better approximation and it will become better and better over time.
So the overshoot will also
Yeah.
become less and less.
Yes.
before it.
Any other question? Okay, in this course, especially in today's lecture and next week, we will use these formulas a lot. I think you have seen these before. These are under the Euler formulas for sine and cosine, and we will use this a lot today, and also maybe in the exercises you have to use them. So I just have them here. Now let's look at this example number 1. So we have, it says that consider 4 periodic function f, which is defined in this way. And first of all, we want to plot f for this specified range, and then we need to specify the basic ground gradient frequency, so we need to identify omega, and then determine the Fourier series coefficients and write the Fourier series of f of t. Let's look at here. What is capital T? What is the period of the function here? It's written there. Yes, please?
Half?
No, it's not half. Any other idea? Yes, please?
4.
It's 4, exactly. Because as I explained it before, I also have it here. When you have a function f of t with a period of t, or for instance 2, you can also write it as a 2 periodic function. So 2 shows the period here. And in this example, we have capital T, which is 4. And also, if you look at the range I have here, it starts from -2 to +2. And from -2 to +2, we have 4 units. I mean, there are 4 between those numbers. So again, it confirms that capital T is 4. Now I need to plot that. Here I do it manually, but of course you can do the plot with Maple, which I will show you also later today. I need to do the plot for capital T smaller and equals to 4. Okay. What is the range of T which I need to plot here based on what is written here? Yes, please?
0 to 4.
0 to 4 is also included, but it's not complete range. Yes, please?
-2 to 2.
Now, again, minus 2 to 2 is included but not completed, yes?
Minus infinity.
Now, actually, I have a point which I asked this question because I know that sometimes the students are confused here. When it says absolute value of t greater or equals to 4, then you have to consider all values of t, which if you take the absolute value of them, and it becomes smaller and equals to 4. Here, it means that the t should be minus 4 and 4. Because in this range, when you take the absolute value of all the numbers in this range, the results are smaller and equals to 4. Am I right? So again, if you see such a thing in an exercise or exam, just keep in mind that this means that I have to do the plot from minus 4 to 4. Now, it says that from minus 2 to minus 1 is 0. So I have 0 here. And then at t equals to minus 1 is half. If 1 is here, this would be half. So we have this point. And then from minus 1 to 1 is 1. At 1 is half. And 1 to 2 is 0. So now I have a plot from minus 2 to 2. But the question here asks for the range of minus 4 to 4. Yes, please.
I didn't understand how you could get the straight line at the y-axis. Which interval did you look
It
at?
says that here, from the range of minus 1 to 1, the value should be 1.
Ah. Okay.
And again, I use this. From minus 1 to 1, which is here, I should have a line at 1. Okay. Any other question before I go forward? I continue. Okay. So this is minus 2 to 2. But I need the plot for minus 4 to 4. How should I do that? Any ideas? Yes, please?
It's a periodic function, so you should just repeat the
Exactly.
values.
That's the point. It's the periodic function. So what does it mean? It means that at 2, again, the new period will start. At the beginning of new period, again, it's 0. Then it's half. And then 1. I stop here. Of course, if it asks for more range, you can continue. Again, 0 here. Half. And hopefully this is 1 as well. Yeah. So when you have a periodic function, it means the pattern will be repeated and repeated over time. And that's why we have the repeated, half of this, because we start at 4, and also the rest on the other side. Now it asks about specify the basic ground frequency. So I need to obtain omega. How we can do that? Any ideas? Yes, please.
2 pi times frequency.
Can you repeat it?
The 2 pi times frequency.
The frequency is here.
Sorry, times period.
So multiply?
Yeah.
No, actually it's divided by capital T.
Yes, 1 time over t.
Yeah. So T is 4, so it will become 2 pi over 4, which is pi over 2.
Oh, it's like
This is pi.
ah, yeah.
So now I need to find the Fourier series coefficient. So I need to find the Cn. We have a formula for it. If I wrote, is it correct? 2. Again, you can also do it from, I don't know, 2 to 6. It's up to you, but I usually stay with the first or the one which is easier for me to see. And then f of t,
Wouldn't it be easier to do it from 0 to 4?
it's up to you if you want to do that. Yeah, I
What
think
do you have
as
in
far as
for
I know, the
zero?
result should be the same.
Alright.
And then e to the power of 0, which is 1 times dt. Now let's look at the range of minus 2 to 2. Minus 2 to 2, I'm here. And when you look at here, you can see here is 0 and 0, so it doesn't have any effect here. So I can rewrite this as 1 over 4, the integration of minus 1 to 1, and then f of t is 1 times dt, which it would be 1 over 4, and this is t from minus 1 to 1, which is 1 over 4, 1 minus minus 1, which is 2 over 4, which is half. So C0 would be half. Yes, please?
How was it that ft became 4?
How capital T became 4?
Just ft, the function ft.
The f of t is not 4, f of t is 1.
Oh, it's 1.
This is 1.
Okay, then.
And why it is 1? Because, again, for the range of minus to 1, we have value of 1. It's given to you here in this middle line.
Alright.
Yes, please.
How come you could take it from minus 1 to 1 instead of minus 2 to 2?
Okay, let me write it here and explain it. Again, one more time. So we have, this is just to make it much more clear. We have the integration of minus 2 to 2 of f of t dt. Here, I don't have a continuous function. I have a discrete function. It is a function which I have different value for different range. So if I want to do it, I can write it as minus 2 to minus 1 of f of t dt plus the integration of minus to 1 of f of t dt plus 1 to 2 of f of t dt. I just opened the whole integral, the whole range. So from minus 2 to minus 1, the value of function is given is 0. So this will become 0. For this range, also the function is 0. So this one will become 0 as well. So the only range which I need to take the integration, the area under the graph, is minus 1 to 1. And that's why here, suddenly from minus 2 to 2, I have minus 1 to 1. Any other questions? Okay, can I erase this? Now, we have C0, which is half. Now I want to find Cn, which it would be 1 over 4 minus 2 to 2 of f of t e to the power of minus I n. I have omega in a formula, and I have the omega, which is pi over 2. So I will put it here as well. Pi over 2 t dt. Again, this minus 2 to 2 can become minus 1 to 1 based on what I just explained that. And f of t is 1 e to the power of minus I n pi over 2 t dt. I put also 1 here. 1 which is 1.
But I don't get how you get pi over 2 and not 2.
The formula for gram radian frequency frequency based on what I have just explained or showed you earlier is this one. In order to find that, I need one more. Yeah. In order to find the omega, this is the formula you have to use. 2 pi over capital T. And capital T is 4. 2 will be cancelled out with one of the 2 here.
Okay.
And then it will become pi over 2.
Okay. Yes.
Because this 4 can be written as 2 times 2.
Yeah.
I mean, it's a multiplication. And these two cancel out each other.
Okay. All right.
Good.
Thank you.
You're welcome. Now, yes. Now I have to do the integration. You can use mental, but because I'm a teacher, I have to do manual. Yes. But let me check if I have everything here. So it will become 1 over 4. Then I put in a bracket. The integration of the exponential, we had a formula before, so or you can use the integration tables or Maple, it's up to you. It will become minus 2 over I n pi e to the power of minus I n pi over 2 t, and I have to compute it for the range of minus 1 to 1. Make this line here. Don't mix this together. Okay. So I just use the integration, yeah.
Oh, sorry. Just, are you allowed to use Maple to do the
For
integration?
the, yes,
for the exam?
yes. Yeah,
Okay.
usually in the last 5 years exam question, which I designed those, I wrote you can use Maple here.
Okay.
But I know that the previous teacher wanted all these manually, but I don't want because you have not learned this from me. So that's why. Yes.
So, no.
Okay. So now it will become 1 over 4. First, here I have to put t equals to 1. Here it will become minus 2 over I n pi e to the power of minus I n pi over 2 because t is 1. Then minus 2 over I n pi. Now t is minus 1. E to the power of minus times minus is a plus I n pi over 2. Minus times minus is a plus. I can make the factorization of these two terms. I mean here, I can make this one and come out of this bracket. So it will become 1 over 4 minus 2 over I n pi which again, these two will be cancelled out with one of these two, so I can make it as a 1 and write this as a 2.
I have a.
Sure?
I need to ask, how do you get minus 2 over I n
Pi? Okay.
You took it down from.
No, this is the rule I use. Again, for integration of e to the power of ax dx, it is 1 over a e to the power of ax. Okay? This is the formula. So your a, where is it? Your a is minus I n pi over 2. So now I have to write it as a 1 over minus I n pi over 2, which if you simplify this 2 comes in a numerator, so it will become minus 2 I n pi.
Okay, that's how you get the 2.
Yes, I just used the formula, nothing else.
No, I was just confused.
How these 2 became up, I mean,
Yeah.
I understand.
Okay.
So I just use the formula and nothing else. Now, here, I have 1 over 2 multiplied by this. Let's back to the Euler formulas I showed you before and see if I can use any of those. E to the power of.
You can put the
I think this is a plus, so this should be plus here. And you can see this is a plus. It should be plus here. And now,
They just have
Sign.
the power
no,
equations to be divided
is
by
it
2i.
this one?
Yeah.
It should be.
No, I think
I think you.
That I and
So if I do this as a minus and minus becomes plus, let me see what we missed. I think I made a small mistake somewhere, so let me figure out.
You could use the minus that's outside the bracket.
Oh yes, you're right. If I multiply this minus inside,
Minus becomes.
because you
it will become 1 over 2, 1 over I and pi, and then e to the power of I n pi over 2 minus e to the power of minus I n. I think it's correct now. Yeah, just multiply a minus with the bracket. And now the signs would be there. So it will become now again we missed the I then. Oh no, it's here. It's here. Yes, sorry. So it will become 1 over n pi, then sine of pi over 2 times n. So now we have the Fourier series coefficients, both C0 and Cn for a general case when for n not equal to 0. Yes, please?
what is 1 over
N times pi.
oh
I have a solution in the slides as well, so if you cannot read my handwriting, you can find it also there. It's here. You can see for C0, Cn as a C0, I got half. And also this is what is for n not equal to 0. So now we have Fourier series coefficients. I need to write the Fourier series general form as well. Did you take a picture? Oh, so now we need to write the Fourier series, and we have a formula for it, which says that f of t is a rough approximation of summation of n equals to minus infinity plus infinity of Cn e to the power of I and omega t.
Yeah, I have a question.
Yes.
So the approximation he did. So it's not possible to ever get it perfect.
If you increase the n as much as you can, it will become every time much more better and better and better.
Yeah.
But of course, because you are replacing or approximating this continuous one with the continuous one, it cannot be 100% the same.
But it can be like
Very close to
Yes.
it, yeah.
okay.
Okay. This, again, because I considered two scenarios, I will write it or to see the effect of it here as well. It can be written as C0 plus the summation of n2 minus, and for n not 0, of Cn e to the power of I, and omega was pi over 2 times t. It becomes C0 was half and Cn here was 1 over n pi sine of pi over 2 times n power of I n pi over 2 times t. And that would be the end of the solution. Any question?
Yeah, I didn't understand.
Which part?
All of it.
Okay, you know, one of the bullet point we had here is that, of course, find the coefficients and write as a Fourier series of f of t. So we need to write it in this format. Here.
Yes.
Okay. Here, this is the summation from minus infinity to infinity. So what I did here, I brought C0 out of this summation. Why I did that? Because e to the power of 0 is still 1, so it can come out very easily. So I did as C0 plus summation of minus infinity and infinity when n equals to 0 is not in the new summation. This is how we read it. N equals to 0 is not, I have a line over it, is not in this summation range because it's there. And then Cn, which is the coefficient when n is not 0, we obtain it here.
But where did you get CO from?
CO is the one we obtained here for n equals to 0.
Okay. And that
I
was-
usually call it C0 and not CO. So for n0, I call it C0.
Okay.
Yeah.
And you got.
And Cn comes from here, which n is not 0. It's written here. And then this is the partial formula which I kept it. I only replaced this omega with the value we had got it earlier. Yes, question?
Yeah, I'm just worried because this function, that's not a continuous function you get, because you got a power function.
You mean the exponential?
Yeah.
I will explain it after the break. I have it
Alright.
here. And,
Alright. Of course.
because now you could see that actually it is also here a little explanation, but I will go through it in much more detail after the break. Our original function is a real function, as you can see, but the Fourier series we wrote is an imaginary or I format, complex format. So again, there is a possibility to convert this to the real format as well, and then you don't have this what we mentioned.
Yeah.
Okay? Yeah. But we will go through it after the break.
Alright.
Let's have 15 minutes break and please take a picture.
Pull the table down.
We'll be back at 9:13.
Pull the fourth table down.